Welcome to another episode of AI on AI, where we delve deep into the intersection of artificial intelligence, innovation, and real-world applications. Today's topic is one that has the robotics community buzzing: primitive prompt learning, or PPL, a technique designed to revolutionize lifelong robot manipulation. Joining me are a group of distinguished experts in AI, robotics, and business strategy. Let's start with a quick introduction to this concept.
Thanks, host. Lifelong learning in robotics is like trying to assemble a puzzle where the pieces keep changing shape. Robots need to handle a variety of tasks in dynamic environments, and they often suffer from catastrophic forgetting. That is, they lose previously learned skills when adapting to new ones. Traditional methods rely heavily on retaining vast amounts of data for replay, which is memory intensive and, quite frankly, impractical for real world applications.
That's a great foundation. Expert in ML, let's build on this. How does PPL actually work? What makes it different from other approaches like experience replay or LoRa?
Sure, at its core, PPL is a two-stage framework. First, in the multi-skill pre-training stage, it identifies and learns shared primitives. Think of these as the fundamental motions or actions that are common across tasks. For example, the act of gripping an object is a primitive that can apply to grasping a mug or a banana. Then, in the lifelong learning stage, PPL optimizes new task-specific prompts while keeping the pre-trained ones frozen.
That's a delicious analogy. Expert in robotics, can you shed some light on the technical aspects? How do these primitive prompts actually interact with the robot's learning system?
Absolutely, primitive prompts are integrated into a diffusion transformer-based policy, which is essentially the decision-making brain of the robot. These prompts are prepended to the keys and values of the multi-head self-attention layers. Think of it as giving the robot a cheat sheet of reusable actions that it can refer to while learning new tasks. What's particularly exciting is the motion-aware prompting mechanism.
That's incredibly insightful. Expert in business strategy, let's pivot to the practical implications. What does this mean for industries that rely on robotics?
The implications are massive. Think about industries like e-commerce fulfillment, healthcare, or manufacturing, where robots are increasingly used for specialized tasks. With PPL, companies can significantly reduce the time and cost associated with training robots for new tasks. For instance, a logistics company could deploy a fleet of robots that learn to handle a variety of packages without needing to be reprogrammed for each new item.
That's a game changer. Expert in robotics, let's go back to the technical side for a moment. The paper mentions something called motion-aware prompts. How does this work, and why is it important?
Great question. Motion-aware prompts are essentially a fusion of optical flow data, capturing the movement of objects in the scene, and semantic task descriptions. This combination allows the system to model both the semantic and motion-shared primitives across tasks. For example, optical flow provides a low-level understanding of how objects move, while the semantic information provides context.
If I may jump in here, this is where PPL's brilliance really shines. By focusing on these shared primitives, we're essentially creating a universal language of robot manipulation. It's like teaching someone the alphabet so they can form any word, rather than teaching them every word individually.
That's an excellent point. Expert in AI, let's talk about challenges. What are the limitations or areas where PPL might struggle?
One challenge lies in the robustness of motion aware prompts, especially under complex conditions like poor lighting or cluttered environments. While PPL is designed to generalize, extreme variations in the environment can still pose difficulties. For instance, in one experiment, the robot had to perform tasks under changing lighting conditions, from warm to cold to dark. While PPL performed admirably, there was some degradation in performance when the lighting became too extreme.
That's a fascinating insight. Expert in ML, let's talk about the future. How do you see PPL evolving, and what are its broader implications for AI?
I see PPL as a stepping stone towards truly generalist robots capable of lifelong learning. As we refine techniques like motion-aware prompting and primitive sharing, we could see robots that not only learn new tasks, but also adapt to entirely new domains. Imagine a robot trained in a kitchen environment applying its skills to a hospital setting. The modular and reusable nature of PPL makes this vision more achievable.
That's exciting to think about. Expert in business strategy, let's bring it back to the bottom line. What should business leaders take away from this discussion?
The key takeaway is that PPL represents a paradigm shift in how we think about robotic automation. It's not just about making robots smarter, it's about making them more versatile and cost-effective. For business leaders, this means investing in robotics becomes less risky and more scalable. The ability to continuously adapt to new tasks without significant retraining or reprogramming makes robotics a more viable solution across industries.
That's a perfect note to end on. Thank you all for this engaging and insightful discussion. As Einstein once said, the measure of intelligence is the ability to change. With innovations like PPL, it's clear that robots are becoming more intelligent and adaptable than ever. For our listeners, stay tuned for more episodes where we continue to explore the cutting edge of AI and its real-world applications. Thank you for joining us, and until next time, keep innovating. Summary of Think Small, Act Big. Primitive Prompt Learning for Lifelong Robot Manipulation. The paper introduces primitive prompt learning, a method for lifelong robotic skill learning. Robots face challenges in transferring knowledge from old tasks to new ones, a process humans perform effortlessly. The study focuses on learning reusable and extensible motion primitives, or basic building blocks of robotic movement. Primitive prompt learning uses a two-stage framework for skill acquisition. In the first stage, robots are trained on multiple skills to learn shared motion primitives. Motion-aware prompting combines optical flow, motion data, with semantic task instructions to identify commonalities across tasks. A diffusion transformer model incorporates these prompts to represent and transfer knowledge between tasks. In the second stage, new skills are learned by optimizing lifelong prompts alongside frozen pre-trained prompts. This approach allows the robot to retain old skills while learning new ones without needing access to previous data. The method was tested on a large dataset of robotic skills and in real-world scenarios using a Franka-Panda robotic arm. Primitive prompt learning outperformed existing methods in both simulated and real-world environments. The approach demonstrated better transfer of knowledge between tasks and robustness under challenging conditions. Limitations include performance drops under extreme lighting variations, suggesting future work to integrate depth and 3D scene data. Implications of this work include more efficient and adaptable robots capable of lifelong learning.